Let us look at a typical type of constraint motion situation wherein, let us say, this is the block of mass m1, this is the block of mass m2. They are kept on top of each other and there is no friction force involved. So here what is exactly happening? So if the block of mass m2 shifts towards the right hand side, let us say this guy shifts towards the right hand side, then the block of mass m1 will have to come down in order to occupy that space. So if the block of mass m2 shifts towards the right hand side with x2, let us say x2 is the displacement of block of m2 towards the right hand side, that the block of mass m1 will have to come down a distance, let us say y1. Now the way in which the blocks have been arranged with respect to each other, when the block of mass m2 shifts towards the right with x2, necessarily the block of mass m1 will have to come down a distance y1, and this angle theta is the constraint. This angle theta has to be maintained always because of the way in which the blocks have been arranged. So you can draw an alternative diagram and say that this block shifted towards the right hand side. The block of mass m2 shifted towards the right hand side. So here the block of mass m2 is like so. Let us say in such a case the block of mass m1 would have had to come down over here. The block of mass m1 would have had to shift over here, let us say. So if the block of mass m2 moves with x2 and the block of mass m1 moves with y1, then necessarily the student should follow the logic that necessarily we'll have to have theta as constant. So we'll have to have this particular equation, y1 upon x2 is equal to tan theta. That is y1 is equal to x2 tan theta. On double differentiating y1, we get the downward acceleration of the mass m1. So downward acceleration of the mass m1 is a1 and the rightward acceleration of the mass m2 is a2. Downward velocity happens to be v1 and here rightward velocity of mass m2 happens to be equal to v2. So on single differentiating, firstly we get down the equation v1 is equal to v2 tan theta, and on differentiating it one more time we can write down the equation a1 is equal to a2 tan theta. So these are the constraint motion relationships. So this is a similar kind of question. So here this is the angle theta. So when this is mass m1, this is mass m2. So basically as the mass m1 is coming down, let's say the mass m1 comes down this much, then the mass m2 will have to shift towards the right hand side. How much will it have to shift towards the right hand side? You can see that it will have to shift towards the right hand side this much. So if this angle is theta, then this angle also happens to be theta. So here tan theta, it's clearly easy to understand that let us say this is the displacement of mass m1, I am labeling it as x1, and let us say this is the displacement of mass m2, I am labeling it as x2. So we can clearly see that tan theta has to be equal to x1 upon x2. Therefore x1 is equal to x2 tan theta. On single differentiating, we get v1 is equal to v2 tan theta, because tan theta is the constraint that is constant over here, and on differentiating it one more time we get a1 is equal to a2 tan theta. So this is a situation similar to the first situation. Now there is no friction involved in this particular question. Okay, here Here is again a similar situation. Let us say this guy comes down this much. This much is how much the rod that is constrained to move in the vertical direction. It comes down by, let us say, x1 amount. So in that case, the wedge will have to shift towards the right hand side. So this is how the wedge will have to move towards the right hand side. So if the wedge moves towards the right hand side by x2 amount, so you can see clearly that this is x1 and the right shift of the wedge is going to be x2. So this, let us say, is x2, and whereas this is x1. So according to this triangle, this is x2, this is x1, and guess what is theta? This happens to be the angle theta. So we can write down, this is the angle theta, this happens to be, let's say, x2, this happens to be x1. Again we can write down the same thing, this is x2. So this wedge has the mass m2, this guy has the mass m1. Okay, so we can again write down the constraint motion equation or constraint motion relationship as x1 upon x2 is equal to tan theta. Therefore x1 is equal to x2 tan theta. V1 is going to be equal to V2 tan theta, and A1 is going to be equal to A2 tan theta. So let us look at this particular rod. This rod is making an angle theta and this angle is 90 degree. So this angle happens to be equal to 90 minus theta. Alright, so let us say if this end of the rod is moving rightward with velocity Vb, let us say this end is B and this end is A. Okay, then this end is moving downward with velocity Va. Now the length of the rod is constant. So basically the component of Va in this particular direction is going to be the same as the component of Vb in this particular direction. This is what we are getting at. Okay, so the component of Va over here happens to be V1 cos of 90 minus theta. So V1 cos of 90 minus theta is going to be the same as, this is theta, so this is theta, is going to be the same as Vb cos theta, because the length of the rod is constant. So along the rod, both the ends of the rod necessarily have to have the same velocity along the length of the rod. Okay, so basically along the length of the rod we may write down V1 cos of 90 minus theta to be equal to Vb. Okay, so yeah, Vb cos theta. We could have labeled this as Va because it is the velocity of point A of the rod that is moving along the vertical wall. So we can clearly see that Va sin theta is equal to Vb cos theta. So here you get Vb upon Va equal to tan theta. So here the constraint is the fact that the length of the rod is constant. So if you want to double differentiate this from, or rather single differentiate the velocity equation, we can write down Vb is equal to Va tan theta, and for the relationship between the instantaneous accelerations we can also, anyway these are the instantaneous velocities, because the velocities V and Vb need not necessarily be constant as the rod is falling down. So differentiating it one more time, we get AB is equal to AA tan theta. So this is the analysis of the falling rod.